Okay, so this is really 10.9 through 10.10. And the textbook, physics textbook, has a lot of other information and applications. We're not going to go too crazy in those applications. We're just trying to get a basic and general understanding. And there's two principles, or really one principle and an application of this formula that we're going to deal with. And this is Bernoulli's equation. And Bernoulli's equation is really good at combining everything we know about pressure and density, and just understanding that as you increase the height of a fluid, there's going to be increased pressure down below as all that weight of that fluid sits on top of it. And so we understand that, if we go up higher in the atmosphere, we have less atmospheric pressure. If we go lower down in the atmosphere, we're going to have more atmospheric pressure. And so Bernoulli tries to piece all this together. But it also understands this principle that if we have fast-moving fluids, that it actually causes a decrease in pressure. And so not only is it about height, but it's also about speed or rate of flow. Because if you think about something like this, you have, in a pipe, you have particles moving every which way, and they're doing their own thing, right? But if we give a push through, okay, and cause all of these guys to start moving this way, what will happen is they'll stop bumping into each other as much, they'll stop hitting the outer walls as much, and we'll notice that there's a decrease in the internal pressure. That all of a sudden, every one of these guys seems to be going generally the same direction. They'll still bump into each other once in a while, but the impacts and the pressure is going to be felt very differently. And so Bernoulli also included in this idea that the velocity of that fluid makes a big difference. And so what we have here for Bernoulli's equation is that the pressure in one situation, one position in a system, plus rho times g times h1 plus 1/2 rho v1 squared. This would be all the different ways we could get pressure will be equal to anywhere else in the system. It's going to have the same quality or total quantitative value of pressure. It's going to have its own, what we call gauge pressure or atmospheric pressure. It's standard pressure that it's under, okay, plus any rho g h2. So what we notice here is if there's a height difference between h1 and h2, there's going to be a pressure difference, and p1 and p2 will pick up that difference. That the actual pressure or gauge pressure on something would be indicated as increased or decreased because of that. And we also have 1/2 rho v2 squared. So here again we see if we speed the air or fluid up in one situation versus another, that we're going to see a change in pressures. And these two sides have to be equal, give us some really important stuff. So first off, rho is going to be the density of the fluid. And this can be applied to a lot of different things. We're going to talk about it basically in two principles. One is the idea of an airplane wing. That's not a very good airplane wing, but we'll call it good. And the idea is that air that's sitting here can travel one of two paths. The path on top is a longer path, but for it to take the same amount of time, this means that this velocity up here compared to the velocity on bottom is going to be bigger. So the velocity on top turns out to be bigger, and because we have a higher velocity on top, okay, if you think about this as the top over here, because this went up, that whole value there went up, the pressure over here would go down in order to maintain balance. And so we would notice that the more speed we have, the less pressure we're going to have. And so we're going to start noticing things like this airplane wing is going to want to go up into the low pressure environment. So with Bernoulli's equation, we can start to describe how much an airplane's wing can support in terms of force. And so that's a really big idea. The other application that we have a lot of is basically plumbing and pipe work. If you think about a big reservoir, and then you've got a pipe going into your house, okay? So let's say we have a bunch of high pressure water here. Okay, let's say we have pressure equals, say, 5 atms. 5 atmospheres of pressure. The reason we'd have all that pressure is because there's a lot of water as we go up into the building. A lot of water pushing down on it. Well, here's the thing. As you go up in elevation, we see that the height difference is going to alter our pressure. Okay. Now, when we think of this H, we're not thinking of how high you are. We're thinking about your depth, if you will. Okay. The deeper you are, the more you're going to have that pressure. And so as we come up here, we're going to have less pressure up the higher we are. It's barely going to dribble out. The water's not coming out of that pipe very good, like it would be down here, where it would be just gushing out if we opened up the faucet. And so what ends up happening is we have to narrow the pipe along the way in order to make sure that we still get high pressure out at different places. And so these are the two applications of this. You need to know that density is the density of the fluid. Height would be your height difference. One thing you have to understand or think about is that, again, as you go up in the atmosphere, the pressure will drop, which, if you think about it, as this goes up, higher you are, okay, the pressure is going to drop there, okay? And so we're seeing these different relationships. If one quantity is taking on the bulk of it, then the other guy's going to have to make up the difference, okay? And so, yeah, as height goes up, pressure is going to drop. So that's Bernoulli's equation, and really cool application problems come from that. Keep in mind that oftentimes we don't know P2 and P1. Oftentimes what we're actually asked to find is, like in the airplane question, we're asked to find the force of lift. Well, we know that pressure is F over A, and in an airplane question, this P is going to be a difference of pressure, or change in pressure, from P2 to P1. So oftentimes we do this as P2 minus P1. We don't actually know what P2 or P1 are, but if we know all of this other stuff, we can set up a P2 minus P1 by subtracting P1 over and moving everything else over. That ends up equaling F over A. So by knowing the pressure difference, we can find the lift, or how much the airplane can hold. Okay. Okay, so that's going to help you with the airplane question. Over here we have our pipe question. Those are just two cool applications of the ideas. Well, Bernoulli's equation can be applied to a very specific situation, a very specific problem, which is where Torricelli's formula comes from. And in Torricelli's problem, we have an open container or reservoir of water. And we're going to poke a hole in it or open up a tap, and we want to know how fast that water is going to flow. Now, a really good application of this would be something like you have a reservoir where you have a lake, essentially a reservoir, and you're going to let water flow through the canal system. Well, what rate is the water going to flow? Well, that depends on a lot of things. And so we have to be thoughtful about the height of the water and where's that reservoir going to. So, you know, if you think about it, you know, oftentimes with a reservoir, we actually open it up here at the height of the water. But if we actually want water to flow at a high rate, we really want to open it up at a lower level. Okay, so kind of think about it. The lower you are, the faster you're going to be moving that water. And so Torricelli's equation says that the velocity down here, call it V1, it'll equal the square root of 2 times gravity times y2 minus y1. Now y2 and y1, okay, y2, y1, it's essentially the height of the water. And so the deeper the water is, obviously it should put more pressure on that bottom water and push it out with a higher velocity. But this is actually just an application of Bernoulli's. If we let H become a Y, and we assume that because this is a big reservoir, that the velocity of the water as it drops, it's very, very slow. And that allows us to call V2 0. So pretty soon we're able to see that there's a height difference here. We can sort of see that 2 for the 1/2 that shows up there. We can see the square root because of the square. We can see the densities canceling. If we assume that the pressure up above is the same as the pressure coming out, or the same as the atmospheric pressure out here, those things end up equaling out, or we don't worry too much about them. We end up with Torricelli's problem, which is great for solving problems where we talk about, again, releasing water from a large reservoir or releasing water from a water tower. How fast is that water going to drain? How fast that water drains tells us a lot about how long it's going to take to refill that. We actually have situations and systems right now where what we'll do, hydro dams are really, really effective at producing electricity when we want it. The problem is you have to have water in there. And so one thing that we've learned is that at night, when the wind is blowing but nobody's using electricity, we can actually pump water up into a reservoir at night and then allow it to flow down and turn a turbine, okay, spin it to generate electricity during the day. And so it gets down there, and then we come over and we pump it back up at night. So we can have this cyclical thing. Now it's not that effective because we do still end up using energy to produce the energy on a pretty significant basis, but it does allow us to have on-demand power. So there are communities where they really rely on this idea of water storage as a way to provide electricity. Well, that question of how fast does it drain is a big deal. We need to know how much energy we're going to get out of that water. Well, depending on how deep the water is, that's going to determine a lot. There are actually times and situations where if the water's not deep enough, we're not going to open it up to produce electricity. We have to have it moving fast enough to actually turn the turbine. So anyway, that's a side thing. It's really neat. I love Bernoulli's equations. I love the concepts of flight. I think it's really wonderful. Hopefully that helps you. I know you're going to have some questions, but just bring them in and let's talk. All right. Good luck. We'll see you in class.